Cool. And we're live. Look at that. 2 live streams back to back. What is this? Christmas? We have ourselves here a MacBook Air. This one's going to be should be easier than the A1990 we worked on yesterday. This one's a A1466. And judging by the board number on here, this is either going to be a 2013 or a 2014 MacBook Air. So the reason we have this one is because it's just not powering on. I have my multimeter software right there. There we are, right there. So let's see how much current draw we are getting with our battery unplugged and everything, the MagSafe board and the I/O board connected. And we're getting 0.02. So normally that means that we are missing PM Sleep S4L, which is a line that's required for getting this computer out of a sleep mode back into just turning on in general. So with these MacBook Airs in particular, what I like to inspect for first is there an obvious short on PP bus or a short on the CPU? That's pretty important because this has a dead CPU. It's not worth repairing. Let's go back to the overhead camera we have here. And so PP bus is going to be right here on this side of that tiny little white fuse. So we're going to put our multimeter, which we still don't have the multimeter software, so we're just doing this analog style with our digital meter. And we're going to measure PP bus to ground. As we can see right there, OL, which means that PP bus is not shorted to ground. Let's just measure across the fuse to make sure that the fuse is actually working like it should. And we have 1 ohm, so the fuse is working. Now what we want to do is check the CPU coils. That's going to be, of course, these giant little inductors right next to the CPU. And we're going to put our black probe on ground, our red probe on the coil. Of course, all this we want to do with the battery unplugged, which I've gone ahead and already done. And we're at 145 ohms. Now, what does that exactly mean? If you're unfamiliar with CPU voltage or CPU resistance, resistance to ground, it usually is going to be a low resistance. So if we were to test this in continuity mode, we might make the mistake of thinking that beep right there might be a short to ground. CPUs always have a low resistance because they have lower power rails. So how do we know exactly what the CPU resistance to ground is on a MacBook, or in this case, this particular MacBook? Well, some technicians at logi.wiki have actually put that information together. So I'm going to go ahead and pull that up here on our... Actually, let's... 1 second. I need to make sure that we're not doxing anyone first. Cool. And... let's go ahead and pull up our on-screen. So logi.wiki, this is very similar to repair.wiki. I would say that logi.wiki came out a couple months before repair.wiki, but this has some more of the complex issues we see with board repair. But there's a section specifically called resistance to ground, and that is a great link, a great page right here, resistance to ground, that gives us all the information of all the different Intel processors' resistance to ground. So this model is a 2013-2014 MacBook Air 13-inch. So it wouldn't be that one, because that is a 2015-2017. So let's keep looking. 2011, 2012, 2013 through 14 MacBook Air. The i5 specifically is around 120, but if this was a Haswell processor, a Haswell H processor, doesn't exist for the MacBook Air. Okay, so this is a Haswell U processor, 2013-2014 MacBook Air i5, and it has a resistance of 120. We were reading around 140. There is room for variance. That is good. Now, if we were getting a measurement around, let's say, 2, CPU would be dead. But it's around 140, says that this should be around 120. But you see if this was a MacBook Pro 13-inch, the resistance is even lower. It's around 53 to 77. So this is a really good reference page for just checking your CPU voltage before diving too far onto a repair. So let's check and measure PP bus real fast. I want to give this a visual inspection, but I just also want to get a mental note of what our PP bus line is actually reading as well. So with the battery unplugged, let's make sure our power supply, DC power supply, is plugged in, 18.5 volts. We're pulling 0.02, and we're going to put our multimeter into DC voltage. And what do we have on this side of our fuse? 8.6. Now, that is a perfectly good reading of PP bus on a MacBook Air. 8.6 is a good number that we're looking for. So, I'm thinking we need to do a visual inspection. And let's go ahead and pull the logic board out for that. This board has not been removed yet, so I'm going to go ahead and start pulling that out. We've already pulled out the SSD, because when testing for shorts, typically I will remove the SSD just in the event that something is shorted. We don't want to potentially kill the drive if data is crucial. What I love about this board is that we have 6 screws that hold the entire logic board down, and then 3 screws that hold the fan. So this is one of the quicker MacBooks to take apart. But what do you guys think this one might be? You think it's liquid damage? Do you think it's random component failure? Missing PM Sleep S4L, if you've watched my videos in the past or other technician videos, usually is going to be an issue around the CPU, the SMC, the clock chip, or the platform controller hub, which is built into the CPU on this model. Also, I like to do visual inspections before I start measuring power rails. It saves a lot of time. There's been several instances in the past where I would start my power rails and measure from like the 12 volts, 8.6 volts, 3.4 volts, and then I eventually would see a pretty obvious sign of corrosion during the sorry, just moving this out of the way. I would see a pretty obvious sign of corrosion during the voltage measurement phase, and realize that we could save a lot of time if we just do a visual inspection first. So now I got the board out. We're going to set the top case to the side, and we're going to change over to our microscope camera. So let's start up here in the CPU area. We can see a little bit of oxidation corrosion buildup. We are in South Carolina. All of South Carolina is a humid environment. There's a little bit more corrosion right there on that inductor, to the point that you can actually see this test point has completely rusted away. So we're probably going to find humidity damage on this logic board, and potentially on the underside as well. Before I go too far, I don't want that rust just kind of escaping since we're so close to the processor. So I'm going to clean that up real quick with some alcohol. The JTAG connection is notorious for getting a little bit of corrosion buildup, and that could make our PM Sleep S4L missing, but I don't believe that is the case. It looks pretty clean. That's the Wi-Fi card, our backlight circuit for our EDP connection. Again, a little bit of corrosion buildup right there, but it's all on the test points. Okay, this side of the board looks decent. So now let's flip this over. Is there our backlight circuit? Thunderbolt circuit looks okay. And here's our SMC. This is not, look at that. There's a little bit of, is that corrosion, or is that? That is just a little bit of corrosion next to our SMC. So we might actually have corrosion underneath the SMC. So we're going to revisit that momentarily. We're going to check and see if the SMC is even being told to turn on. Okay, here's our clock. There's our BIOS. Our BIOS has a little bit of corrosion on our test point. Now, this could be the cause of our issue as well, because if this test point is too corroded, it will actually prevent this resistor right here from communicating to the BIOS, or the EFI chip, specifically on this model, the EFI chip. Let me clean that up as well. Just don't want rogue rust floating around on the board. And I'm cleaning it with 99% isopropyl alcohol, so that's going to evaporate. A little bit of schmutz right here. It's very, very tiny on the back of the CPU area. There we are. That's going to be why it's not turning on. Now, all of these tiny little resistors are on the back of the CPU. So as mentioned, a voltage reading that low we saw earlier, the 0.02, means this is pulling such little power, it's not even getting told to kick on any further than in just the off status. It's not going from a state 5 or S5 to an S4. Now S5 just means that the computer has power, but it is turned off. S4 is and S3 are usually sleep and hibernation. I don't know what S2 and S1 is, but S0 or SO, state 0, is the computer is turning on. Missing PM sleep S4L from previous repairs we've learned is going to be CPU, PCH, which is built into the CPU, the EFI chip, the clock chip, or the SMC. There are other things it could be, but those are typically the main things that we want to look for. She's got that. So we found a little bit of corrosion on the back of our CPU. Let's check and see exactly what those components are. Let's pull up our on screen. We need to minimize logi.wiki, and now we're going to look at the back of our board. Want to have it in the same orientation as that how we're looking at it. And let's revisit in the microscope camera exactly where we're at. Okay. And let's look for this same thing in our board view software. So here we have a couple of capacitors in the same area of where the corrosion is at. Let's look again. Yep, right there in that corner. So around here in this general area is where our corrosion's at. Excuse me. And so what we want to look at specifically is going to be this cap, these components, and that component. Let's look and see what those are. So we have ourselves PLT reset L. I forget what the PLT stands for, but I do know that if this is being pulled down, it is it's missing, or if it's shorted to ground, which it could be because we're right next to ground right here, this will prevent the entire computer from turning on. It talks specifically to the CPU. This is our PP3v3SO. Which is responsible. This goes specifically to SSD power enable, and then this one is PP33S5, which goes to PCIe wake low. So what we're going to do is we're not going to measure if these are present. We're just going to replace this entirely. So let's go to our microscope camera, and what I want to do first, actually, I need to document the repair. Timeout. I'm going to have to actually just pull this up so I can save this on the customer's ticket information. I just don't want to dox them. That way, if this comes back in the future, I know exactly where the issues, the corrosions was at, and we can revisit that in the future. Knock on wood. People hardly ever come back after we fix their boards, but we always want to make sure that we document everything. So, let me pull this up here. Microscope camera, and then I just need to screenshot this. Okay, sorry. I just needed to document that. before I actually did anything else. Okay, perfect. So let's go ahead and let's dive straight into this repair. So what I'm going to do first is actually clean this area up with a little bit, tiny little bit of Windex on a Q-tip. And then I'm going to follow it up with some alcohol to evaporate the water that is in the Windex. And then we're going to hit this with some flux. And we're going to use some hot tweezers to replace those tiny little resistors with. So let's get our rework station, our 861DW working. And let's turn up the air and the temperature. And let's increase this. We're behind the CPU, so we don't want to go too crazy in heat. And then the most important thing, fume extractor. We want to make sure that as we heat this up with flux and use leaded solder, that we don't inhale any fumes, any cancerous fumes. All right. Now let's go ahead and start with these resistors. We got 1, 2, this one's almost welded itself down, and 3. Now the pad on that last one I removed is pretty much non-existent, so we're going to have to clean this area up, get it prepped for us to put the replacement resistors from a donor board. So we're going to go back over it with a little bit of isopropyl alcohol on a Q-tip. And you can see right there that pad is pretty much gone. Not necessarily it's gone, it's just so corroded that we're going to have to use a scalpel to expose the copper. Because the pad is still there. It's just hiding. This one right here also looks a little suspicious. We're going to revisit that one if this doesn't turn on. And clean it up. And let's see. Do we still have, are we missing copper entirely, or is this all just some schmutz? It does look dirty, but I also think we are actually missing some copper. So, what we're going to do now is use our scalpel to expose some of the copper of the trace that it's connected to. And you can use yourself a brush, a tiny little wire brush, or the back end of a razor blade or a scalpel. And yeah, after we're exposing more of that copper, I can see it's not that it's just dirty, it's just completely removed. And it looks like that is actually connected to, it looks like there may be a via hiding underneath there, which is just a test point or a point that goes through the layers of the logic board. Let's try scraping just a little bit more. That may not be a via right there. The via is actually right here where that test point's at. So now what we need to do is put a tiny little wire that's going to connect all three of those points. Yeah, that's pretty much gone. But not to worry. Let's expose just a little bit more copper for the traces that are right next to this test point. And then now I'll be right back. I just need to go get some jumper wire. And I have two different types of jumper wire, one that I use for MacBooks and one that I use for iPhones. Let's see how the MacBook jumper wire is going to fare. It may be too thick, and we may have to end up using the iPhone jumper wire. And I think that's the case. This looks a little bit too thick. Let's see. And it's enameled as well. Let's compare it to the iPhone jumper wire. Where are we at? The iPhone jumper wire is so tiny that I can hardly ever see it. It almost looks like hair. Yeah, you see, you can hardly even see it under the microscope. I'm going to go with the MacBook jumper wire just because it's a little bit thicker. I don't want to go with too thin of a connection because the thinner the wire, the more it acts as a resistor. And that can affect data lines, voltage lines. So now, let's go ahead and put a little bit of new solder there to prep us for our wire. So I'm going to switch out from our micro tweezers to our micro pencil. It's just a really, really tiny iron. And I got a knife tip attachment on it right now. And what we want to do is tin up these copper points that I've exposed. Make them a little bit more silver. Man, I need to get a better camera. Alrighty. Now let's go ahead and get this wire. We're going to use a tiny little bit right here. You know, this is going to be way too big actually. We are going to have to go with the iPhone jump wire instead. So let me time out for that. Alright, and now my hands will stop shaking. We're going to attach that right there. Another one right there. And we're going to bring it around town. We're making like a boomerang shape right here. Okay. And then I'm just going to put a tiny little dab of solder right in the middle to kind of form a little pad. Very, very tiny piece right there. Okay, so it's not pretty, but once I get the replacement resistor on there, it's going to look a lot cleaner. So now we need to cut off the excess wire. And how we do that is we take our scalpel, and then we get our wire here and just wiggle it back and forth until it eventually fatigues like a paper clip bending too many times. There we are. So now we need a donor board. We need a donor board that doesn't have corrosion in the exact same spot. Unfortunately, my donor board that I currently have has corrosion in the exact same spot. Be right back. Hey, how's it going? Doing all right? We'll be right with you. Let's see, we have plenty of 2015, 2017 boards, which would work, but they have components in a slightly different spot. All right, got a donor board. Switch back over to the microscope camera. And it's those three tiny little resistors in the center is the ones that we want. So I'm going to start with the one that we were working on, the jumper wire, first. Just go ahead and get that out of the way. And I forgot we changed out to a pencil, so I need to go back to the tweezers. And wait for a beep. Alright, we have a beep. We have resistor. Okay, let's get this lined up. We're going to line that up right there. It's going to be a little crooked, but we'll put a little bit of mask on it afterwards so it can't move. Hello, Serge. Good to see you again. Let's tin up this side. And then now, we need to put some solder, and the door's just going off all of a sudden. Now we're going to put some more solder on the right side where our wire's at. That's not what we want it to look like. Let's try to clean that up just a little bit. Well, we have a big blob of solder there, so admittedly it is going to try to form a giant blob. Which, it will work. There we are. So we have a piece of wire, just in case, acting as like a rebar, and it is connecting this part of our trace to the point right here that this is soldered onto, to this part of the trace as well. So that is successful. Now let's go ahead and remove or finish transferring over the easier resistors, now that the hard part is out of the way. Okay. I don't want... And this one, I think this one was for the SSD enable line. This is our PP3B3S5 to SSD enable. Alright. And then this one was our PLT to something to do with the CPU. Or PLT reset. I had to connect to a line on the CPU. Whoops. Let me change hands real quick. Okay. Now that that's partially lined up, we're going to use our hot tweezers and just pinch the sides of the resistor. Oh, whoops, wrong side. Sorry, hands are a little shaky right now. Now that those are in their homes, I'm just going to touch up where the pads are actually soldered onto so they don't have any mountains. They have nice mounds. Okay. And then while we're at it, let's go ahead and put a little bit of solder on this one oxidized test point where it looked like a resistor would be. Probably not important, but we're right next to it. Come on, hands, don't fail me. And you know, for good faith, that one capacitor did have a lot of corrosion on it too. Let's go ahead and replace that. Now, since the capacitor has ground on one side, I am going to use my rework station to heat up the general area as well, while I pull up with my tweezers. The ground is actually on the top part of the capacitor. There we are. Another stream? Cool, says Pedro. Those caps and resistors are in fact tiny. Yep, especially since we're dealing with the back of the CPU. There are going to be various voltage and data lines. I'm just going to try to make that a little smoother. Now this is our ground connection, so that is going to require a little bit more heat. I am going to put just a little bit of leaded solder on there so it melts a little bit easier. At least try to. There we are. And now let's pull from our donor board again. And where were we? We were working in this area. Alright, so same method. We're going to use our hot tweezers to grab the capacitor. We're going to use our rework station up here where the ground is north of the capacitor. That comes right up. And back to the patient board. And like before, let's align this up. And then now what we have to do is we're going to grab the capacitor again while we heat up the area. My hands want to work with me. It's probably going to go on crooked. There we are. Now let's clean that up, make that look a little prettier because it's a little crooked. Man, it is really blurry for you guys. Let me see if I can focus that a little bit. Put a little bit of flux down and touch up both pads on the capacitor with a little bit of solder. Now, I'm really trying to avoid using too much heat because we're on the back of the processor. Processor doesn't like getting too hot. Okay, so now that we have some solder mixed with it. Let's try touching it up one more time. Ah. And clean up these mounds, these mountains that we have here. We want them to be a little bit more smooth. That way they're not rigid and pokey, pointy. We're good there. And we're good there. And let's put a little bit more solder on that one resistor that connects PLT to the CPU. And we added just a little bit of solder onto this capacitor, but that's all right. All right. Now before we clean up this area, let's see if that actually fixed it. We need to take the daughter board out of the frame so that we can connect it. That way we can inject power into it. I guess not necessarily inject power, but we're just going to connect our power supply to it. All right, did we get it right the first time? Or are there other resistors in that general area that also need to be replaced? Okay, DC power supply is on. We already have a light on that, so that's just because of this type of connection. Let's see what we get as far as voltage amperage consumption. And we still have 0.02. So unfortunately, that didn't fix it. Just to make sure this isn't a weird loose connection, because this is a custom cable that I cut up from another charger. Still 0.02. Now there was a little bit of corrosion next to our SMC, if you remember that. But let's check for other resistors in that area, because admittedly we haven't even measured that side. We just replaced the obviously damaged components. I think we're going to have to clean this area up just so that the camera can actually focus properly. So for cleaning up flux, I used a little bit of 99% isopropyl alcohol, and then I'll follow it up with some acetone nail polish remover. Then we can use our rework station to evaporate what's left. Okay. And let's measure. So we have about 1,000 kiloohms, 97,000 kiloohms, so that's probably supposed to be 100. And 9 kiloohms. So let's go ahead and reference that real quick. Oops, missing PM sleep S4L. That's kind of what it looks like. We'll double check that here in a moment. So let's check with our schematics and see what we had. So this was around 1. Correct. This was around 100. Correct. And then this was around 10. Correct. So all that seems right. So now let's measure some neighbors. So up there in the top right corner, see what we have here. It's about 10. 10 seems like a normal reading. That is 1. And then let's look at you, because you were also in the line of corrosion. About 100. So all that seems about right, but let's go back and double check. Oh, whoops, sorry. I never changed my, my camera view. So that was about 1. Let's see, we measured right here. 100, and then we measured this one too. 10. Okay, so that all seems normal as well. However, do we have a solid connection for that one resistor? because it looks like it's pretty rusty actually right here. So just to make sure we actually have a proper connection, what I'm going to do is I'm going to put my multimeter in resistance mode and measure from that scratched copper right here. And yeah, it's 100 kilo ohms, so that seems fine. And let's just keep probing some neighbors to see. Don't probe your neighbors, but we're going to probe the resistors over here to see if there's anything that seems out of spec. That one says 92. That seems a little low. I'm sure that's supposed to be about 100. That one's at 100. That one's at 10. 100. 100. 10. So all those are reading like normal voltages or normal resistant readings. Have 100. 2.2. Or I'm sorry, hold on. I think that's a 22. I don't think there was a dot in between. Yeah, 22. That's a weird reading. So what is that? $22. Nope. It's just a weird reading, but that one's right. And then it looks like that we still have some corrosion around this capacitor. Let's just make sure there's not an obvious short right here. And we're in the mega ohms, so we're fine there. Do we have continuity between this capacitor and this resistor? So we should have some sort of measurement across. We have 10. So yep, that looks like that trace is still perfectly fine. So hopefully we didn't get any type of event here that ended up killing or damaging part of the CPU when it touched ground. Let's revisit down here because we have some more oxidation. One says 91, 90, and I think these are supposed to be 100. So I think just for good measure, we're going to go ahead and replace these. And let's check and see exactly what those are. So those are near our test points. See, I went pretty far down on that. So it's this resistor right here. It's about 100. And then this one, but that has to deal with LCD. This has to deal with AP, Wake Select AP, which goes directly to the CPU. So let's just go ahead for good measure and replace that. Yeah, it looks like the soldering iron went to sleep. Oh, this is really on there. So whatever this is, going to the AP line, which connects directly to the CPU, it's actually so corroded, it almost looks like it fused itself to the pad. So we're going to have to use a little bit of our heat with this as well. And what I'm going to do is just go ahead and wick up that pad. Okay, there we are. And then we're going to put some fresh solder down. And let's go back to our donor board. And just to measure, are these actually saying 100 or are they off as well? That one says 93. This one says 92, which is very similar to what we were getting. So that might actually be okay. Okay, so there's one. Into your home. Okay. And 2. Let's get that resistor all nice and lined up. Alrighty. And truthfully, since the resistors that we pulled from were reading about the same reading from the donor board, I doubt we're going to have much of a change. So let's just confirm that is the case. Let's go back over to our DC power supply. Plug that in. And what do we get? 0.02. I could have the strange thing is the fact that we don't have any difference at all. Let me make sure this charge is working. I'm going to plug it into a working MacBook right next to me. Yeah, we're getting 2 amps on a working MacBook, so there's still another issue why we were missing. And now that we've been talking about it, missing PM Sleep S4L, let's just confirm. Pretty sure we know that that's what's going on. Whoops, wrong screen. And we're going to do a quick search for PM_SLP_S4L. And that's in several spots. Let's see, in this general area, I have that one resistor that's very close to where we're at, so let me see where that is located. There you are. And go back to the microscope, and it's this one, that tiny little resistor right there on the left-hand side. Plug in our power, put this into DC voltage reading, and then check and see what this tells us. And as we expected, we are missing PM Sleep S4L. Had a feeling that's what it was going to be. So now, to make sure there's no short, we're going to put this into resistance, and we're reading about 16 kiloohms. Alright. We might actually have to do some intense troubleshooting here. Now, I think that this one resistor that we had to put a wire right there may actually have a via connected to it. Let's check and see if that was the case. So, if we touch here, it looks like that this is also going to connect to U8020, which is responsible. What are you responsible for? You look like you're responsible for converting PP3V3S5 to PP3V3 sus. I might have that backwards. Yes, that is the enable line for PP3V3 sus enable. But let's see. It is directly connected to the backside of the CPU, it looks like right there. However, where it's at, I would like to think, was that one test point, which we can't see here, but there was a trace coming off this resistor. So hopefully that would be our via, not a test point, but our via that goes right here onto the CPU side. There's really no way to definitively confirm that. So now I'm just kind of doing a little bit more inspection in this general area. So with that type of damage, I guess the question is, did it look like something was spilled onto the computer, or did that look like humidity damage? Oh, hey, there we are. There's a little bit more stuff right there. And I think that is actually a thermal sensor that's directly connected to the CPU. This looks like something was spilled into it. You can almost see the outline of where some residue, some liquid was in here. So this looks like there are signs of humidity after something was spilled onto the computer. So I think we're just going to have to replace that as well. Yeah, I mean, this is just giving me a weird measurement in general. This is a capacitor. That side's ground. This side, it's kind of all over the place. I mean, you can just look at this thing. It looks pretty bad. So let's just go ahead and remove that as well. This one I'm not going to worry about cleaning up with Windex. I'm just going to go ahead and pull it off with some heat and flux. But this is either our CPU thermal sensor, or this is our fin stack, or fin thermal sensor, which would make more sense because on the underside of this is the actual heat seek fin. And the thing is, like, when stuff gets spilled onto here and starts to gunk up, it really corrodes or just eats away at the metal, at the rust. So this one, capacitor, is not wanting to cooperate. There we are. Go ahead and clean that up. And like we did earlier, let's go ahead and remove some of this oxidation here so that we can get a better surface area of the pad so that a new component can solder onto it. Now we want to tin it. Put a little bit of flux down. Let's get the big iron out. Wait for a beep. And let's clean up that residue that was left behind. Yeah, you can see it's just removing the top layer of the board right there. So whatever this was there for a while. So now, let's go ahead and put a little bit more flux down so that when we start moving our other components on, it'll transfer over pretty easily. Let's go to our donor board and make sure that that component is still there. It is. And let's see exactly what that is before we actually replace it. Keep pulling up the wrong scene. Let's see. It is U7840. What is U7840? 1.05V sus LDO. Cougar Point requires JTAG pull-ups to be powered at 1.05 when suspended well is active. That has to deal with internal stuff that we don't use any of the JTAG programming, but it is nonetheless a oh god, what is it? A limit dropout or low dropout? It's supposed to drop 3.3 volts to 1.05. So this is an important power rail regardless. And fortunately, our donor board does in fact have that. So let's just cover this thing in some flux and borrow it. Yeah, it looks like that's some grime. I think that came off the other board. I think it was still stuck onto my tweezers. Okay. Sorry for those who might get seasick, motion sickness from just moving back and forth really quick. The left side of the pad looks good. Let's get the right side. Switch over to our hot tweezers and just touch up those pads real quick. They look good. And now we're going to transfer over that capacitor. Capacitor's extracted. And then let's add just a little bit more flux so that we can put a tiny little dot of solder on the right side of that capacitor since it was pretty oxidized. That was the pad that we had to clean up. Awesome. Okay, I'm just looking at the overall connection on there, so let's see, did that change anything? By restoring the 1.05 sus LDO, did that bring any life back into this? Still 0.02. So there's still another issue. We're finding all the obvious signs of damage, but there's still something that we haven't addressed. Now, when we started looking, we did see a little bit of stuff right next to the BIOS. And what we want to do is test the continuity between the resistor on the left and the pin on the EFI. I keep calling it a BIOS, it's an EFI. And we do have continuity. It just looks disgusting, but this is communicating like it should. And then that's our clock chip, which looks like, it's hard to tell if anything's been spilled onto it, but it does look a little messy around that area as well. Let's check and see if we actually have our clock, if that power line is there. And that's usually a 3.3 volt line. So if we go to our clock, which is right here, we're looking specifically for PPVRTC G3 hot. So let's connect our DC power supply. Put our multimeter into DC voltage reading. And we have 3.3. So the clock is putting out the right voltage like it should. So now we're at the point to where could it be something else like the SMC, for instance, because we did have a little bit of debris in this area. That one component looks a little bit burnt out. So let's measure that real quick, and then we're also going to look back and see if our SMC is getting the right power lines. Keep messing up. Okay. SMC CPU in iSense. That is supposed to be a capacitor reading 0.22 microfarads. And using our multimeter, whenever we measure across, we're getting 1 mega ohms, which tells us that capacitor is capaciting. It is working like a capacitor. But where we had some debris right there, let's check and see that our test point didn't get too corroded. So where's my scalpel? We're going to etch away the copper right there to see if that the actual trace is still there. We're not etching away the copper, we're etching away the top layer of the board. And yeah, that looks pretty solid. So then let's measure these resistors then right next to it, just because that is where we had some oxidation buildup. .5, 18. So 4.5 thousand and 18,000. Let's go back to our schematic and see what these are supposed to be. 4.5 thousand. 20,000. I'm going to measure one more time. That's at 18.9. Oh, but if I measure it the other way, we're at 20,000. So that seems to be fine. So now let's pull the board back and try looking at an angle to see if we can see any signs of corrosion underneath the SMC. Because this might be one where we have to reflow it. Alright, couldn't see any obvious signs of corrosion, so now we're going to measure and see if we're getting the right power lines, or the right voltage line for the SMC, to make sure that SMC is actually being told to power on. So let's go ahead and look at U5000 on our schematic. And what we're looking for is going to be our PP3V3S5 SMC VDA, as well as our PP3V3S5 AV Ref SMC and SMC Reset L. We're going to look at all of those. So this is supposed to be a 3.3 volt line, and that is located right here on this inductor, this coil, to the right of the SMC. So in order for us to measure if it's actually getting the right power, we need to plug in our DC power supply, get our multimeter, and it was this inductor right here on the right side. And what do we have? We have 3.4. That is close enough. Okay. Now what we want to measure is PP3V3S5 AV Ref SMC, which should be in that same area. There's a capacitor right next to it. .298. That's pretty much 3.3. So that's close enough. All right. And now let's make sure that this isn't in a reset. We're looking for SMC reset L. And we have resets right here at R5100, which is that tiny little horizontal resistor. We have 3.4, so we're not stuck in a reset, which means the reset chip is working like it should. Now, when I was just mentioning the resets, it did kind of remind me that our PLT reset resistor was the one that was pretty damaged. So, I'm curious, do we even have PLT reset, or do we have a PLT reset L? Because if it's missing or it's low voltage, then that means that this is telling the PLT to be stuck in a reset mode. Nope, and we have 3.3, so that's not the case. It's getting the right voltage. Okay. I don't know if that was a via that's right there. Because the fact that nothing has changed leads me to believe that we might have to scoot over that resistor some. Let's unplug power because we don't want to do any work with the power plugged in. What I'm going to do is scoot it over a little bit to the left, closer to where the pad used to be. Oh, come on. And then try to put that back down. All right. Now, my theory, the reason I did that is because I think that there might have actually been a via underneath that pad, and I was soldered to the traces, the jumper wire I fixed, but not soldered to the via, if there's a via. I'm hoping there's not a via. Okay. Let's check and see if our amperage consumption changed at all when we did that. Nope, still exactly the same thing, 0.02. So, obvious signs of corrosion. Let's check and see, is there anything else, any other signs of corrosion? Are we missing our all-sys power line? Because that is very close to that same area. Looks like we had some stuff right here next to the backlight circuit, so I'm going to look at the backlight circuit at an angle. And it's mostly dust, not necessarily corrosion. Might this be an SMC issue? I have a replacement SMC. If that is the case, it would just be weird because we had so much damage near our actual... There's a lot of solder balls coming out of the side of that EFI. There was a lot of corrosion on the back of the CPU area, so I would imagine that's where our issues would be. That's been repaired over there. CPU thermal sensor. Let's reference our photo just to see if I cleaned up something that may have also looked dirty. So 1 second while I pull up that photo again. Okay, so this is what it looked like before we did any work to it. And we replaced this capacitor, this resistor, that resistor, and this resistor as well. But we can see that this one up here, that guy, and that were also dirty. But when we measured across them, they seemed fine, so we might have to remeasure again in case I missed something. Let's see, let's minimize that and go back to that general area. It was right here. And okay. PCH SU, what is that? Susac L. That was that one pad that looked a little suspicious, but we touched it up real quick. That has to deal with RAM configuration, so I doubt that has anything to do with it. SSD power enable, BP333, that was an area, but that wouldn't prevent the computer from going into an S4 state. And then we said, let's look at that photo one more time. I mean, yeah, that one resistor right there did look a little oxidized. So that might not be making a good contact, but we did measure across it though. Because when we measured across it from here to here, we're getting 10 kiloohms because this is a 10,000 ohm resistor. So there is a good connection between there and there. This one's a little difficult. We're not going to be able to test to see if this is turning on because that is once it goes into an SO, but we were able to test. Make sure I'm looking at the right component. Yeah, PLT reset L is actually this one down here. I measured this line, which is PP3V3S5, which connects directly to PCIe Wake L. So by this being present, we're telling now PCIe Wake L. So I think this turns on when this is low, the PCIe. But what we're looking for is the PLT reset L, which is right here. Is this present? So I measured the wrong thing. All right, I'm having 0.035, so that's pretty low. So this device still thinks it's stuck into PL. Hold on, let me pull that back up. 1 second. So the device is being held down with PLT reset L. So this is stuck in a reset state. XDP CPU reset low. Where is that? That is some sort of J connector that we can't really access. That's a test point. So this resistor technically isn't important because that's part of our JTAG connector. So really what we're looking at more is why is this stuck in a PLT reset L state? What other resistors are you connected to? You're connected to R1621, R1639, and then you go directly to the CPU and then all the way over here to this as well. So I guess let's measure across R1621 since you're directly connected. It could have had some sort of domino effect. So that is this component right here. $99, and that sounds like a normal reading to me. I need to move this up here in OBS, so I stopped doing that. Okay, there we are. So 99, so I would imagine this is going to read about 100. Sorry, yeah, it does right here. Completely missed that. And then let's go down to R1639, which says it's supposed to be about 100 as well. This resistor is a little bit harder to find. And it's right there. We're reading about 92. Let me flip over my multimeter in case I'm getting a bad reading. Yeah, I'm getting 99, so that's perfectly fine. So that leaves us with this connection, and the CPU itself could be pulling it down, putting into a PL reset state. Let's take a quick look over here. Now, is it a situation to where there's something wrong with the CPU, which is why it's stuck into a PL reset? Or is it because there's something else like bad SMC, for instance? Yeah, I don't see any obvious signs of damage on this one. Super tiny bit of corrosion right there next to the clock. Or, sorry, that's not the clock. That's, I think, a clock for the SMC. Okay. Well, there was a little bit of corrosion next to the SMC. Let's see if the SMC is getting warm. So, we're going to use our thermal imager real quick to inspect to see if the... excuse me. We're going to check and see if the SMC is getting warm. This thing always sounds like a race beginning. Okay, so that is our PP bus generator, which I would expect that to be getting warm. That's not jumping out at me. That was crazy warm. And so far the SMC doesn't look super warm. Like, it is getting a little warm. But that's just because it's getting 3.3 volts, I would imagine. And that's the part of the charging circuit down there, or that's the PP bus generators on the other side. Okay, we're gonna reflow the CP or the SMC. I'm sorry, we're gonna reflow the SMC because there was corrosion next to it. So if there is any corrosion underneath the SMC, this will allow for a better connection. I don't like reflowing without having a definitive answer. Reflowing is such a please bro thing to do. It's not really a good diagnostic, unfortunately. But let's go ahead and start by removing the edge bonding. I guess in theory we could also check and see what voltage the PM or the PLT reset is supposed to be, and see where it's generated from. I hope it's not a situation where it's all being generated by PM Sleep S4L, and it's supposed to be low because we're missing PM Sleep S4L. It's a whole what came first, the chicken or the egg situation. But we've seen that happen before. Okay. And actually, before we do that, there's a very common chip, the All-Sys Power, that is known for getting oxidized on this model, and then we had a lot of corrosion. So I'm just checking to see if maybe that had any signs of corrosion. But it looks like it's on there. So I think for now, that's okay. Alright, let's go back. Clock chip does look like it did get something on it though. That's reflow, and then we may have to just end up replacing that clock chip because it does look like there was some residue over there at some point. Been waiting for a stream like this for a while. I'll just watch the upload. Sorry for doing it so late. Thank you for joining, though. You really don't see that many board repair videos anymore, board streams. It's just, in my opinion, getting a little bit more difficult with the T2s, the Apple Silicons. They're just harder devices to work on, so not as many people, including myself, are really confident to stream these anymore. Okay. But good old A1466 computers, I'll stream all day. Now that we have our flux underneath there, let's go ahead and heat up this area. I'm actually going to move this a little closer to the fume extractor. I can smell too much of the burning flux. Alright, we have 30 minutes to figure out what's wrong with this before we start closing. So hopefully we can get this taken care of before the end of the day. Alright. Ready for this thing to start dancing. Basically just waiting for it to heat up enough to where I can poke it and it just wiggles some. There we are. All right, it moved. So now we're going to rapid cool it. Cool it down using the fume extractor. And I'm just thinking to myself while this is cooling down, I already forgot, but I need to double check to see what the resistance to ground is on PP3V3S5. Because at this point, I think that's what we need to start doing, is just measuring the S5 rails to make sure they're all present, and it's not something silly that is preventing the rest of the rails from turning on. Because it looks like this particular resistor that we replaced with the jumper wire is also connected to U8020. What is U8020? That is a 3.3 sus switch. So that converts 3.3, or I'm sorry, yeah, PP3V3S5 to PP3V3 sus. This should be cooled down enough. .02. So something did change. We went from 0.022 to 0.02 when we touched the SMC. This one may actually have a bad SMC. That was the only time we've done something where it actually changed amperage consumption. Now, it is very little, but that's probably it. Why can't it be something easy? That's fine, it's fine. Alright. I'm just gonna check and see if the general power rails are still there. Let's start with that. Let's do the easiest thing we were supposed to do and look up power aliases. Okay. Do a quick search for power aliases. Here we are. Now, we already confirmed that PP bus was 8.6 volts. However, that was before we started doing everything. So let's make sure that's still working. Yeah, it's still got 8.6 volts, so that's fine. Let's look at PP bus or PP3V3 G3 hot. And that's going to be connected up here. We got PP3 or 3.43, so that's close enough. PPVRTC G3 hot we measured earlier, but that was before we started doing a whole bunch of things. Again, I completely forgot because I'm just all over the place. Probably should still replace the clock chip because it looked a little suspicious, like something was spilled onto it. .3. Nope, wrong one. PP5ES5, which is on the backside anyways. .5 volts, so that's there. PP5ES4, which we're pretty confident is not going to be there because we were missing PM Sleep S4L. And that's correct. So there's no need to check and see if PP5ESO. Why do I keep doing that? PP5ESO. No need in checking that out. Let's make sure PP3V3S5 is present. Tiny little test point in this area we can check. Kind of if it wasn't covered in mask. End of the day customers are coming in. Ah, here, right next to the clock. .3. I'm gonna get this right one day. PP3V3S4, we're pretty sure it's not there because we're not going into an S4 state. That's right. So then PP3V3 sus is not going to be there, so we don't need to check SO. We're not really too concerned at the moment about SSD because that is part of an SO line. I guess we could check and see if 1.05 is restored. That may be a line that turns on later, so we may be still missing that. Yeah, that's not present, but I think that line's supposed to come on later on down since it's a suspended line. And then that's backlight, that's Thunderbolt, that's CPU V-Core, so we're not concerned about any of that. Okay, so at this point, this is where we just start throwing chips at this to get this guy working again. The clock chip looked a little suspicious. It might be working. We're going to replace it. We're going to go ahead and replace the clock. And then if that doesn't work, we might have enough time to replace the SMC before the end of today. So the question is, does this have a good clock chip? It looks like it does. So let's get to it. The crystal also looks like it's got some junk around it as well. And the crystal we could test with an oscilloscope. We could also, just for good measure, replace it anyways. Let's do that. Let's take care of the clock and the clock crystal. Where did my tweezers go? Oh, there they are. Okay. And as I'm burning this, I can definitely smell something like some sort of drink coming off of this. So that also begs the question, did something get spilled in this area of the board that may have killed the clock, but also potentially the EFI chip? I'm gonna have to mute my mics for a second since a customer's calling. Back, and just had to answer a phone call real quick. Is that a clock divider next to the crystal? I don't know. Like the resistor next to it? Okay, so our board's still a little warm right now. So I'm gonna cool it down. Inspect to make sure that all those connections look fine. That one pin on the right side of the clock looks a little suspicious, so what I'm going to do is heat this area back up while holding the clock down, and we should see balls of solder start to come out of the side. Actually, we're not getting a good joint like I thought we would. So I'm going to just pick that whole thing back up. I'm going to lay it back down. Here we go. That laid down and went into place like it should. Let's touch that up. And now, I'm going to cool this down. No, the chip you changed. The divider. I'm not sure if it's called that. Do you mean driver, by chance? That was the original one. I was curious why we... it looks like we replaced that one already, back in June. Yeah. So the chip that I replaced, it was the clock driver chip. So the crystal and that chip is the clock itself. Okay, let's see. We had a spike there for a second. That was different. No, and we're still going around 0.02. Alright, so the fact that after we touched the SMC, we got a different amperage consumption. It's very small, but we were consistently getting 0.022. Now we're getting 0.020 after we touched the SMC. So something around the SMC or the SMC itself has gone bad. It is 5:40. We close in about 20 minutes. Let's see if we can get this SMC replaced in time. I have an SMC conveniently in this baggie. I don't think it's balled though, so we're gonna have to reball this chip. Let's go ahead and get that done right now. Yeah, it definitely is gonna need to be reballed. Alright, it's going to be one of the quickest SMC reballs that we've ever done. First, let's start off by just wicking up all the solder pads, or all the existing solder. Alright, now that that's done, we're going to take a little bit of alcohol and clean up the SMC. SMC has been cleaned, and now we're going to put this in our reballing stencil. So let's go get that. All right. So we have this very handy stencil kit, and this one specifically is for the SMC. Now you can use balls, like solder balls, and there's a magnet on the other end here that's supposed to hold the balls in place as you heat it up. But I've actually found that using a little bit of solder paste mixed, or just solder paste entirely instead of the solder balls, for the SMC at least, is very, very helpful. When doing RAM upgrades, then I use the solder balls. Okay, let's get this in focus and make sure that it's in focus for you guys. It is, and now it's out of focus. Okay, and then now we're gonna grab some thermal paste. And let's go ahead and spread this across like a solder PB&J sandwich. I need a little bit more solder paste than that. Okay. Let's put just a little bit more right here in this bottom corner. Fantastic. Solder paste is prepped, ready to go. Let's clean up the residual flux that's built into the solder paste with a little bit of a Q-tip. We want it to be a little dry so it doesn't move too much. Now, to make sure that our solder balls don't jump out of place, we're going to drop our output of our air, as well as the temperature. We don't need it heating up too quick. Okay. Now, let's heat up this area. And we're going to start far away, just going around in a circle, heating this area up. Okay, now that this area is warmed up, whoops, keep hitting the microscope. We're just going to get a little close to it, but not too close. I want the solder balls to melt to the chip. And what tends to happen is that the solder balls try to form balls and then jump out of their little pockets. rather than actually solder onto the chip itself. Like down there in the bottom right, it's trying to jump out. But it looks like the rest of the balls are properly soldered on except for that bottom one. We had one just jump out right there, a rogue one. So let's see if we can push that back in. Okay, that solder ball is back in its home in the bottom right corner. Let's get this one down in. Okay, and all of our solder balls are done. Now we need that to cool down for a second before we actually extract the SMC. So I'm just removing it from the magnet. Let's see if the balls have cooled down. They have, so now I should be able to lift this out from, or push this out from the backside. And now we should be able to actually extract the SMC from the stencil. You may have to heat it up some though, because it looks like the chips, or the solder balls, are really holding this thing down in place. So let's heat this up with just a little bit of air. 1, 2, 3, 4, 5. And I'm just starting from the corner and just kind of working my way in. And it's really not wanting to move right now. Heat it up just a little bit more now. 10 minutes left on the clock. Can we do it? Okay. Okay. I'm just separating from the backside. And now I should be able to start pushing the chip through. Just really try not to damage the chip. Okay, just gonna lift it up here from the side. Okay, and let's go again, but from this angle, there we are. And did all of our balls stay? Yep, we didn't lose any balls in the... And I don't think we damaged the chip. I think we just made an indentation in it. Okay. Put a little bit of more flux down. Now we're just gonna have all the balls melt again. Perfect. Our reball was successful. So now we have to remove the SMC off of our board that we're working on. Get this in focus. Get this covered in a little bit more flux. Ooh, actually, before I forget, we want to mark part of the board too, just so that we know how to align it up. And so, what I'm going to do is take my blade here, and I'm just going to put a little corner piece into the board. Very little bit, not enough to actually cause any damage. Just enough to have some sort of marking of where this lines up. I'm just lightly scratching the top layer of the surface. And I think I actually broke the tip of my my scalpel here, so I don't think it's actually going to cause too much of a scratch, which is okay. That actually kind of works out. Okay. And now let's turn our temperature back up. And go ahead and start extracting this. Five minutes left. We got this. Okay. Look on the bottom side of the SMC for any obvious signs of corrosion. Nothing immediately is jumping out at me. Don't really like that. Alright, now we need to wick up all of our pads here, so let me get a new piece of wick. Alrighty, now that all of our pads have been wicked up, let's clean this area up. And you can kind of see my outlines, my scratches in the corners, just to help me position the replacement SMC. Let's go ahead and put down some new flux. Gonna heat it up so that it becomes tacky, not as fluid. And actually, the top left corner where I marked kind of looks a little deep, so I'm just going to make sure that I still have continuity across. We do, okay. Just wanted to make sure. Now, the orientation is, it looks like it's an upside down arrow. So we want to line this chip up. And we're going to use the edged corners that I have here to help me square this up. I think we are good as far as alignment, so it should just pull itself into place. So now I need to turn my air down. Let's go to 60. And then let's start from far away like we were doing when we reballed. Just a little bit of flux right there in the bottom, so that way it can slide underneath it. A little bit more. And we're just patiently going around the surface area, waiting for something to wiggle. There we are, keep going. Add a little bit more flux. Align up the bottom right side a bit. Perfect, the whole chip just moved into place. So now we can go ahead and turn up our air. We'll max it out actually. And we'll just heat it up for a good minute. Alright, and the chip is wiggling like I expect it to be, which tells me that all the actual solder pads, solder balls, have soldered respectfully onto their pads. There's 6 o'clock on the dot. Let's see if this fixed it. So just to revisit, while we're waiting for this to cool down, this one had a little bit of corrosion right underneath the SMC. Or I'm sorry, let's start from the get-go. This one had a little bit of corrosion right underneath the CPU. There was 3 resistors in particular that looked like they were affected, and one of them that I'm most concerned about was a PLT reset, which is directly connected to the CPU. After replacing that, it still didn't resolve anything. We actually still had the exact same amperage consumption of 0.022 amps. We then discovered a little bit of corrosion right next to our 1.05 sus enable line. Replaced that, still nothing. The clock chip looked like there was some sort of residue around it, like there was some liquid in the past. We replaced that, still nothing. The only time we ever got any change in our amperage consumption now, it was very, very little. It was 0.02 of a difference. We went from 0.22 amp consumption to 0.20 amp consumption was after we reflowed the SMC. There was a little bit of corrosion around the SMC. So we've gone ahead and we've replaced it, hoping that the SMC may have just died. Now, moment of truth. .022. So we've restored that, but that didn't fix the issue. So, if I had to guess what's going on here, because I think we're at our limit. We've been streaming for 2 hours. Admittedly, we only charged $250 for this repair. So we're at a point to where this has become no longer an economical repair. Since it's a 2013-2014 board, a board replacement would be the next thing to advise. But it almost looks like the corrosion on the back of the CPU may have actually damaged something on the CPU. Some sort of data line, some tiny internal fault. So I'm going to chop this one up to being ultimately an internal CPU issue. I think that we won't be able to spend any more time on it, but instead quote out for a board replacement. So I hope this has been kind of informative of just kind of troubleshooting from start to finish, of looking for visual inspections, checking the resistance to ground on the CPU, as well as just checking different power rails. Pedro, I understand. I feel the exact same way. But ultimately, that's the end result for here. Troubleshooting PM Sleep S4L is always a very troublesome one because it can be any of the main vital components on the MacBook that's preventing it from turning on. So I hope this has been informative. You know, we win some, we lose some. Unfortunately, we lost on this one. But yeah, thanks for joining me. I'll see you guys in the next one.